In this video, we're going to continue our discussion on derivatives and learn two more rules, the product and quotient rules. These rules will allow us to take the derivatives of products of functions and quotients of functions, meaning that we'll be able to do derivatives of more complicated things than we've already been able to do without using the limit definition. So we're going to start this video by just asking a question. Is the derivative of f times g equal to the derivative of f times the derivative of g? Your first instinct might be that, yeah, that makes sense, but unfortunately, this is not a true statement, and I'm going to show us an example of why this does not hold. So you would say no, and for example, let's use f of x equals x and g of x equals x squared. Then f of x times g of x is equal to x times x squared, which is x to the third. So the derivative of f times g is equal to 3x squared. But if I take the derivative of f and the derivative of g separately and multiply them together, I'm not going to get that same result that I should get. The derivative of f is the derivative of x. Derivative of x is 1. And the derivative of g is using our power rule from the last time. 2 comes down and multiplies onto the x, and the new power on the x is a 1. So this tells me the derivative of f times the derivative of g is 1 times 2x, which is 2x. So the 3x squared that we got by multiplying our functions together first is not equal to the 2x that we get from taking the derivatives separately and multiplying them together. So this is sort of bad news. This just means that we are unable to find the derivative of a product by taking the derivative of each piece individually and then multiplying the results. However, there is a nice product rule that we can use to find the derivative of a product. It's a little more complicated than just multiplying the derivatives together, but it's still not too bad. So let's learn our product rule. Our product rule says that the derivative of f times g is equal to f times g prime plus g times f prime. So it's the first function times the derivative of the second plus the second function times the derivative of the first. And let's do an example right away to see this in action. Let's differentiate y equals x squared times sine of x. So this is a product rule problem because I have the product of x squared and sine x. So in my product rule, x squared is going to be my f, and sine x is going to be my g. So using this product rule, I now know that the derivative of my y is equal to the first guy times the derivative of the second guy plus the second guy times the derivative of the first. And we just have to fill in our parentheses. So this first set of parentheses is supposed to be the derivative of the g. So derivative of sine x. The derivative of sine we learned in the last video. It's cosine. And my next set of parentheses needs to be the derivative of my f. Derivative of this x squared uses the power rule. 2 comes down, and then I have x to the first power. And this is the derivative of this function. I'm going to rewrite it a little bit just to make it a little prettier. And we get x squared times cosine x plus 2x times sine x. And this is our derivative using our product rule. Not too bad. Let's do another example right away just to get the hang of this product rule a little bit more. It's going to be a little more abstract than the example we just did. So in our next example, if h of x is equal to x times g of x, and g of 3 equals 5, and g prime of 3 equals 2, find h prime of 3. So we need to find the derivative of this function h, even though we really don't know much about h at all. H is equal to x times some function g, and we don't know what g is. All we know is that g evaluated at 3 is 5, and the derivative of g evaluated at 3 is 2. So we are going to be able to do this problem still. You just have to not be scared by it. So h of x is x times g of x. I am multiplying there, so it's going to be a product rule. And in my product rule, the x is going to be my f, and g is, well, it's going to be g. So my product rule says that the derivative of this function h is going to be the first guy times the derivative of the second guy, plus the second guy times the derivative of the first. And the derivative of my second function is the derivative of this g of x. I know that's g prime. The derivative of the first guy is derivative of x, and we know from our last video that that is 1. So this tells me that h prime is equal to this expression. I have h prime of x is equal to x times g prime of x plus g of x. And I'm wanting to find h prime of 3. So let's just plug 3's in for all the x's and see what happens. 3 times g prime of 3 plus g of 3. But we know what g prime of 3 and g of 3 are equal to. That was given to us in our problem. Our problem said that g prime of 3 was equal to 2, and g of 3 was equal to 5. And so when I just do the arithmetic that's left, I get 3 times 2 is 6, plus 5 is 11. So even though I don't really know what the function h is, I know its derivative at 3 is equal to 11. All right, so that was our second product rule example. And now we need to learn our quotient rule. And the quotient rule, quite frankly, is my favorite rule of all of them. So here is our quotient rule. The derivative of a quotient of functions, f over g, is equal to gf prime minus fg prime, all divided by g squared. So why in the world would this become my favorite derivative rule when it looks very complicated to remember? Well, because there's a really, really dumb little trick for remembering how it works. So here's my trick for you. I'm going to call the top of the function pi, and the bottom of the function low, which makes sense because the top is up high and the bottom's down low. Then I'm going to translate this in terms of high and low. So I would have low and then the derivative of the high. So I'm going to say d high to be the derivative of the high minus high d low to be the derivative of the bottom. Square the bottom, and away we go. So our quotient rule becomes a sort of math hoedown, if you will. The derivative of the quotient is low d high minus high d low, square the bottom, and away you go. Is that incredibly lame to remember it? Yes, it absolutely is. But you know what? It also helps you memorize it. So I would suggest you memorize it this way because it sticks in your head a little better. I originally memorized it myself with all these F's and G's and primes, and it was very difficult to memorize. And then I learned this trick, and it was much easier. So let's do an example using this new quotient rule. So let us differentiate the function y equals x squared plus x minus 2, all divided by x to the third plus 6. So you can see that this is a quotient rule problem because I have a quotient of polynomials here. I have x squared plus x minus 2 as the top, x cubed plus 6 as the bottom. So the top, there's my high, and in green, there's the low. Now let's find this derivative using our brand new quotient rule. My derivative should be, let me put a bunch of parentheses to fill it all in. There. All right, my quotient rule says that we have low d high minus high d low, square the bottom, and away we go. So I have filled in the low and the high and squaring the bottom. All that's left to do is fill in the d high and the d low, which are the derivatives of the top and the bottom respectively. So I had low d high. I need the derivative of high. The derivative of the top, I have derivative of x squared, which is 2x, and derivative of x, which is 1. And I would have the derivative of minus 2, but that's just 0. And then I have my minus high d low, the derivative of the bottom. Derivative of x to the third is 3x squared, using my power rule. Derivative of 6 is 0, so I don't need it. And this is my derivative already. That's all there is to it. And I strongly suggest that unless you are told to simplify your answers, it's going to sound crazy, but don't bother simplifying it because this is already a correct answer. However, if you are told to simplify, I would suggest that you do all of your distribution on the top, combine your like terms, but leave the bottom alone. So let's go ahead and simplify this one just to get the practice in. So simplified, we're just going to distribute everything on the top. So I have x cubed times 2x, which is 2x to the 4th. X cubed times 1, which is x cubed. 6 times 2x, which is 12x. 6 times 1, which is 6. And now I have my 3x squared times x squared. That's going to be 3x to the 4th, but it's negative because of my minus sign in the front. 3x squared times x is 3x to the 3rd, but again, it's going to be negative. And 3x squared times that negative 2 is negative 6x squared. But watch out, because I have this other minus sign, so it ends up being positive 6x squared. And all of that is still over my denominator squared. And now to fully simplify this, I just have to combine my like terms across the top. So when I combine my x to the 4th, I have 2x to the 4th minus 3x to the 4th. So that's negative 1x to the 4th. When I combine my x to the 3rds, I have positive 1 minus 3 is minus 2x to the 3rd. I only have a 6x squared. And then I have a 12x and a plus 6. All over x to the 3rd plus 6 squared. And here is my derivative. Now, was that a very complicated derivative? Yeah, kind of. But can you imagine doing this without the quotient rule? Picture using that original function and doing that f of x plus h minus f of x all over h and taking the limit as h goes to 0. That's not a good time. Quotient rule is way better than having to use that definition. Let's do another example. Let's find the equation of the tangent line to y equals the square root of x divided by 1 plus x squared at the point 1, 1/2. Well, the first thing I'm going to do is I'm going to rewrite the square root of x as an x to the 1/2, because I know that will make my life a lot easier when I'm trying to use my derivative rules. So first thing I'm going to do is rewrite y equals x to the 1/2 power over a 1 plus x squared. Now, what rule are we going to need on this one? It's a quotient rule because I have a ratio of fractions here. So I have my high, and here's my low. I need to take a derivative because the slope of the tangent line is given by the derivative. So let's use our quotient rule to find this derivative. My derivative is equal to low d high minus high d low, square the bottom, and away we go. So we have low d high minus high d low, square the bottom, and away we go. And now we just fill in the missing pieces. What is d low? Well, d low would go over in this spot here. Let's do d high first. Low d high. D high is the derivative of the top. Derivative of x to the 1/2 power, I use my power rule. I get 1/2 times x to the negative 1/2 power. Remember, you have to subtract 1 from the exponent. And now my d low, for the high d low, is the derivative of 1 plus x squared. Derivative of 1 is 0. Derivative of the x squared is 2x. This is my derivative. But let's try to simplify it just a little bit. Actually, I have changed my mind. We can simplify it if we'd like to, but we also know that we're eventually going to want to plug in our x value to find the slope. The x value that we have to plug in is a 1, and 1 to any power is still 1. So I think it would be much easier if we just plug the 1 in to the unsimplified form and simplify afterwards. So y prime with a 1 plugged into it. If I plug a 1 in everywhere, I get 1 plus 1 squared times a 1/2 times 1 to the negative 1/2 minus a 1 to the 1/2 times 2 times 1 all over 1 plus a 1 squared squared. And that looks pretty terrible still, but remember, 1 to any power is going to be 1. So my derivative at 1 is equal to, this is 1 plus 1, so that's 2. This is 1/2 times 1 to any power is 1, so that's a 1/2. Minus, this is 1 times 2, which is 2. All over 1 plus 1, which is 2, squared. And we can still simplify that even further. My y prime of 1 is equal to 2 times 1/2 is 1. 1 minus 2 is negative 1. And 2 squared on the bottom is 4. So I get a negative 1/4 for that derivative. This is the slope of my tangent line. So now we have the slope of the tangent line, and they gave us the point, and now we can just use point slope form to write the equation of the tangent line. So we had our slope is negative 1/4, and the point was 1/2. So this means the equation of the tangent line in point slope form, y minus y1 is m times x minus x1. We just fill in a 1/2 for the y1, negative 1/4 for m, and 1 for x1. And that right there is the equation of my tangent line. It just happens to be in point slope form. If you're asked to put it into slope-intercept form, you would distribute the negative 1/4 and add 1/2 to the other side, which would get you y equals negative 1/4 x plus 3/4. Either of those answers is acceptable. They're both the same exact line. All right, so now we have learned our product rule and our quotient rule and had a couple examples of each. But now we're going to learn derivatives of some more of our trig functions. Last time we learned the derivative of sine and the derivative of cosine. We are now going to use all of our knowledge to find the derivative of tangent. So let me just call tangent f. I'll say f of x is equal to tangent of x. And the first thing we have to think of is, what is tangent equal to? We have to remember our trigonometry here. Tangent is the same thing as sine over cosine. So my function is sine of x over cosine of x. And I can now find the derivative of this because I know the quotient rule, I know the derivative of sine, and I know the derivative of cosine. So using our brand new quotient rule, the derivative of sine over cosine is low d high minus high D low, square the bottom, and away we go. So I filled in everything except for the derivatives in my quotient rule. So what is in this parentheses here? D high, the derivative of sine. Derivative of sine is cosine. And now my next set of parentheses is D low, the derivative of cosine. Derivative of cosine is negative sine. So that looks like a pretty terrifying looking formula for a derivative, but we can simplify this. So in the numerator, I have cosine times cosine, which is cosine squared. And I have a negative sign times sine, but it's being subtracted. So that makes it positive sine squared, all divided by cosine squared. Now, what is cosine squared plus sine squared? That should be a trig identity that you're really familiar with. It's everyone's favorite trig identity. Sine squared plus cosine squared is 1. So I know that the numerator of this derivative is 1. So I've now found out that the derivative of tangent is equal to 1 over cosine squared. Another way to write that is that the derivative is equal to secant squared. And there we go. So we just found out that the derivative of tangent is equal to secant squared. And now that you know that, you don't have to go through the whole quotient rule procedure each time you see a tangent. You can now just use this as fact, that the derivative of tangent is equal to secant squared. So let me write down all of the derivatives of our trig functions. We already know from the last time the derivative of sine is cosine, and the derivative of cosine is negative sine. We just discovered that the derivative of tangent is secant squared. You could figure out this other derivative over here in a similar fashion, but I'm just going to tell you the formula. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant times tangent. And the derivative of cosecant is negative cosecant times cotangent. So there are your 6 trig derivatives. And I would suggest you memorize all of these. You can see there is a slight pattern. They're paired up in the way that I wrote them. Derivative of all of the co's give you a negative. Derivative of the ones that don't have a co in their name are all positive. And you can see the relations between the two. So I would suggest you memorize all 6 of these. There are a lot of calc classes out there that really expect you know the derivative of sine and cosine and maybe tangent, and then they just kind of leave the others alone. If you are a student in my class, that's not the case for me. I love using secants and cosecants and everything. So you need to make sure you know all of them. Let's finish this video up with just one last example. Let's differentiate f of x equals secant of x over 1 plus tangent of x. So first we need to figure out what derivative rule do I need. Of course, I need the derivative of secant and I need the derivative of tangent, but in general, I also need a quotient rule because I have a ratio of functions. So the derivative using the quotient rule is my low times d high. I'm going to need more room than that. Give me a second. We'll start way over here on the end. All right. So we have the derivative is low d high minus high d low, square the bottom, and away we go. Okay, let's fill in the missing pieces. What is d high, the derivative of secant x? The derivative of secant x is secant x times tangent x. And then I have my d low, derivative of 1 plus tangent x. Derivative of 1 is 0. Derivative of tangent x is secant squared of x. So this is my derivative. And if you're not told to simplify, this is the answer. However, I am going to take the time to simplify this just a little bit, make it look a little bit better. So what I'm going to do is in the top, I'm going to pull out a common factor of secant of x. So when I pull out the secant x, I'm going to have a 1 plus tan x plus tangent x, distribute that. So I'm going to get a tangent squared of x and a tangent x. And I also, when I pull the secant out of this piece, I'm going to have a minus secant squared x. All over 1 plus tangent x squared. And this can be simplified if you know all of your trig identities. So I'm going to do a little reminder of a trig identity for you. We know that tangent squared of x plus 1 is equal to secant squared of x. That means with a little manipulation, tangent squared minus secant squared is equal to -1. In my problem that I have up top, I have a tangent squared right here and a minus secant squared right there. So I can replace those two things with a -1. That gives me that my derivative is equal to my secant x times a tangent x minus 1 all over 1 plus tangent x squared. And that's about as simple as it's going to get. I personally actually would have left my answer the way I had it before, right after just doing the quotient rule. I personally usually do not simplify my answers. I know that sounds like blasphemy, but unless I need to use it for more work, it's a lot easier to not do that. So I tend to leave it unsimplified. You should always do what your instructor happens to like. I personally don't require my students to simplify their answers unless I say it in the direction. So those of you who are currently in my class, if you have a quotient rule problem on an exam and I don't say simplify, you can leave it right after you do that low d high minus high d low business and just stop and put a box around it and you're finished. That's all I have for you guys today. Next time, we're going to learn yet another derivative rule called the chain rule. But for now, just work with this power rule, constant rule, all of our trig derivatives, product rule, and quotient rule, and get real good with them. Get lots of practice in. If you have any questions, feel free to drop them below. If you're a current student of mine, you can email me, or you can come to office hours, and I'd be glad to help. And I will see you guys in the next video.